It is now my pleasure to introduce and announce Boris Koichu. Boris is an associate professor at the Weizmann Institute of Science in Rehovot, Israel, since 2017. Before that, he worked as a PhD student, postdoctoral fellow lecturer, and assistant professor at the Technion in Haifa, also Israel. Boris is a highly respected expert in problem solving and problem posing research all around the world and a regular participant of international conferences, where I got to know him several years ago and am happy every time to meet and discuss with him. We have 40 minutes for the presentation and questions afterwards. Boris, thank you for joining us. I'm looking forward to your lecture.
Thank you very much, Benjamin. Thank you very much, all the organizing committee, for this opportunity. It's a great opportunity in these strange times, and just seeing so many familiar faces is a reward. So let me try to share screen. Do you see the presentation?
Yes, we do.
Yes. So what you see hopefully now is the title of my talk. And in this talk, I'm going to relate several things, including problem solving, problem posing, Olympiad problems, teaching, and teacher preparation. To make this work a bit easier, let me start from an opener. And as an opener, I want to use a particular task. The story is this, that some years ago, I was looking for a nice task to include in one of my courses with mathematics teachers. And of course, it's perfectly reasonable that competition movement is alive because of this wonderful and creative production of new problems every year. The same can be told about assessment. But actually, in regular teaching, I don't need to pose problems every time when I teach. So I just looked at some books in my office, and in one of them, you see the reference at the bottom of the slide, I found the miscoping task as follows. Two students attempted to solve a quadratic equation, x squared plus bx plus c equals 0. Although both students did the work correctly, the first miscopied the middle term and obtained the solution minus 6, 1. The second student miscopied the constant term and obtained the solution set 2, 3. The question is, what is the right solution? Something catched me in this problem, but actually it's not a particularly difficult or challenging problem for mathematically educated people. I guess that some of you already see the solution. Let me wait for several more seconds. Two students miscopied, but in a very particular way. One student miscopied middle term, another student miscopied the constant term, but what we know is their solutions. Do you see it? Anybody? Something in the chat? Okay, we all know that complete silence in Zoom is creepy. So let me assume that with a little more time, many of us would see the following strategies. Actually, we know the roots of the solution of the equation that has been actually solved by the first student. So we know the equation. The roots of the first student were minus 6 and 1, which means that he correctly solved this equation. We also know that he miscopied the middle term, which suggests that we know now the constant term, minus 6. The same about the second student. His roots were 2 and 3, So we know the equation. We know that he miscopied the constant term. So now we know the correct middle term. So just by copy paste, we can reproduce the correct equation, which was x squared minus 5x minus 6 equals 0. And now we know the answer to this problem, which is minus 1, 6. Nice. Probably a bit technical, but in the context of teaching quadratic functions and quadratic equations, it's a good opportunity to talk about the connection between the roots and between the coefficients of the equation. But something was bothering me. What we have in this task is too many integers, too nice, and somehow it was strange. Indeed, from my being a schoolboy, I remember that when you solve a nice quadratic equation, you can change the sign of the middle term without particular troubles. But actually, when you change the sign of the constant term, for many times troubles begin. For example, x squared minus 3x plus 2 equals 0. 1 and 2 are integer roots, but if I change the sign, I immediately get irrational roots just because of discriminant. Another example, actually examples of one equation with integer roots, you can find many, but I was trying to find a pair of such equations so that changing the sign of the constant term would not be a troublemaker, and I couldn't. I spent more than an hour trying to compose such a pair of equations and eventually convinced myself that this is a good case to delve a little deeper into the problem. So, as is technically very simply to understand, if we solve these two equations and want the roots in both cases be integers, the key is some particular property of a discriminant. So I formulated for myself what I called later a double perfect square tasks. Actually, what I'm interested in right now is to find all, or at least some at the beginning, pairs of non-zero integers, b and c, so that b squared minus 4c and b squared plus 4c would be perfect squares. Again, trial and error failed me. I couldn't find any additional pair of such equations in a reasonable amount of time. So how can we approach such a task? Well, all I had in my hands was this one particular example of a pair of equations from the miscopying task. And when looking and looking and looking at these numbers that appear in solutions of this equation, I paid attention to 7, 24, and 25. What is special about these three numbers? What connect them? I see that something is going on in the chat. And indeed, it is a Pythagorean triple. It was just an occasional observation, but somehow it encouraged me very much. I felt that I have whole structure in this problem and came back to the problem while hoping to see somehow these footprints of Pythagorean triples. Well, it was still difficult for me, and for a while I decided to leave this problem and to concentrate on a simpler one, a particular case when one of the discriminants would be 1 and not just any p squared, like in a problem, like in equations from the miscopying task. Well, I am interested in B and C, so I manipulated this system and got that to find B and C, I should say something about S, about this parameter, the second discriminant. I cannot solve it numerically, of course, but it's quite obvious that S cannot be any number, any integer. And the first quite obvious observation is that S is supposed to be an odd number. Indeed, if S is even number, I cannot get B as integer. So what would be the consequences of this simple observation that S is an odd number? Actually, like a good schoolboy, I just inserted this S into the first equations. And after quick manipulations, I got that B square equals K square plus K plus 1 square. And here I felt eureka. Why eureka? This is the system of all the constraints that I have so far. But I see that the key to the solution to this problem is indeed Pythagorean triples, but not all Pythagorean triples. Pythagorean triples in which two smaller numbers are consecutive numbers, consecutive integers. Well, generation of Pythagorean triple is a well-known realm. We can find readily how we can do so. So I tried. The first and probably most famous Pythagorean triple is 3, 4, 5, sorry. And in this case, if K equals 3, I can compute B equals 5, first equation, S equals 7, and C equals 6. Just by substituting the parameters with these numbers consecutively in this system of equation. So B is 5 and C is 6, which gives me exactly the same equation I was beginning from. It is the pair of x squared minus plus x plus minus 6 equals 0. Well, nothing new so far, but what a wonderful feeling of understanding a bit a mechanism behind the generation of such pairs of equations. My next step was obvious. In the internet, we have these endless tables of Pythagorean triples, and I just looked at this table until I found the second triple in which two smaller numbers are consecutive integers. So what equations can be generated from these? The same procedure. I know K, so I know B, so I know S, so I know C. And finally, this gives me a new pair of equations, x squared minus 29x plus minus 210. And indeed, this equation, this pair of equations have integer roots in spite of the troublemaker, which is changing the sign of the constant parameter. Wow, I was so delighted. And of course, I couldn't understand why I couldn't find such an equation by trial and error. I didn't go so far. And I can continue. I can go to the next triple of this structure, and the next one, and the next one, and continue actually as far as I wish with generating these pairs of equations. Let me stop the presentation for a second and ask you what you do when you discover something like this. Anybody? Well, my natural impetus was to share. And I talked with some of my colleagues, and they liked it. it's not a serious investigation and cannot publish it in a mathematical journal, but it was a nice continuation of the problem. My next step was to show it to teachers, and luckily I have access to teacher communities and teachers that I teach in my courses. And when I told this story to the teachers, I actually got two types of responses. The first one was unique because it came from just one teacher. I call him A. He said, "Nice, but this is just a particular case. Actually, you asked about all such pairs of equations, but solved them only for a particular case of p equals 1. But I have additional pairs of equations of the same properties. For example, x squared minus 10x plus minus 24 is a pair of equations with integer roots. And these equations cannot be generated by your algorithm of using special Pythagorean triples." "Wow," I said. How did you get these? There's a lot of room for further investigation. So indeed, it's not an end of the story. We can continue from here. But the most common response was this: "Nice, I'll use the demoscoping task in my class." But well, for me, the demoscoping task was just a trigger for something more interesting for me. And I gently asked, "And what about the double perfect square tasks?" And the usual answer was, "Nice, but too advanced for my students." This opener leads me to the following slide. A big part of the rationale for existence of competition movement is that it has a unique position between regular mathematics education and mathematics research. I know that our colleague from Latvia, Agnis Anzans, called the problems mathematics of competition movement like advanced elementary mathematics. It is still advanced, but it's still elementary. But there are two ways how competition movement can diffuse to other realms of mathematics. The first one is the connection between competition problems and serious mathematics research. There are many cases when, first of all, problems of international mathematical Olympiad level were composed by research mathematicians as particular cases of problems that they try to pursue in their real research. There are also opposite cases when some competition problem was generalized and led to serious mathematics research. I saw here Avi Berman, and we have a common paper in which Avi provided such an example of Olympiad problem, which was generalized and found its way to serious mathematics. So this connection somehow works. But what about this connection? For many times, what becomes appropriate to using in regular mathematics education is just very little of what competition movement can offer. And this problem bothers me. Let me share with you this metaphor. If we think about a pyramid with many, many regular students and some students who are Olympians, it is difficult to expect this diffusion because cultures are quite different, norms of study are quite different, and even persons involved are quite different. Here we have problem committees like we've heard in the panel before me, and expert problem posers and expert mathematicians and enthusiasts who are ready to work with gifted students. Here we have many students whose study is frequently constrained by preparation to exam, by strict curricula, by other norms of study, and by other profiles of their teachers. In this case, I think that if we look at this pyramid in this way, it is little hope that something can be changed. But there is an elephant in the room. Actually, there are teachers who, under some circumstances, can act as brokers between Olympiad mathematics and regular mathematics. This is just an assumption, but teachers, theoretically speaking, are people who are mathematically educated, sometimes having a degree in mathematics, knowing students, interested in challenging mathematics, and so on and so forth. So how can teachers be brokers between regular mathematics and Olympiad mathematics? Let me now introduce something that I call observations from research on problem posing, because so far I talked about Olympiad mathematics and regular mathematics. So an idea that problem posing is a counterpart of problem solving, and thus it is a very important activity, is promoted for quite a long time. Experiments conducted more than 20 years ago show that under some circumstances, mathematics teachers and mathematics students are capable of creating good problems, cognitively demanding problems. Research also shows that such cases are not very common, because in many problem-posing experiments, processes of problem posing can be quite interesting, but the resulting problems are not always interesting. We also know during these years of research which sorts of open-end of problem-posing tasks give us more hope that the resulting problems would be of good quality. Again, I am talking not about problems posed by experts, problem committees, or textbook writers. I am talking about problem posing as an activity in regular education. So we know now that it is better to offer open-ended tasks for problem posing, to engage learners and teachers in explorations, and it worked better somehow than we propose a problem posing task, something like create a story for which solution one would need to multiply 3 by 22. Such structured problems are less interesting than more open explorations. And of course, in spite of actually some accumulated disappointment about quality of problems which are posed by not experts, there is a broad consensus about positive effects of problem posing processes, problem posing as an activity in which both students and teachers can be engaged. There are studies that argue that problem posing has positive effects on creativity, conceptual understanding, problem posing skills, problem solving competences, and also attitudes towards studied mathematics. So a broad consensus that engaging not expert in problem posing activity can do some good. But Ellerton in 2015, while reviewing a long history of problem posing research, observed that in spite of the recognized benefits of problem posing as an activity, it is still relegated to the fringes. And Michal Klinstern, in her PhD study, found that when being aware of the benefits of problem posing, teachers engage in this activity as a last resource. It is easier to look for a problem from endless collections than to pose the problem by herself. They do it anyway as a means of producing for their classes problems of special characteristics when such problems are unavailable somehow. For example, I look for a problem for opening a new theme, and I want it to be exactly adjusted to the strength of my class and connect to particular mathematical idea. If I have such specifications, it is indeed sometimes easier for the teacher to combine several problems into a new one than to look for a ready-made problem. So it's no wonder that problem posing is still relegated to the fringes. Again, Olympiad movements is alive and requires production of new problems. Regular teaching, not necessarily, and for many times teachers have very pragmatic attitude to posing, creating their own problems. So from here, I would like to add that actually teaching for problem solving is perceived by many teachers as a natural part of what they do. They, of course, think not necessarily about Olympiads, but they think about preparation for a challenging exam. So to prepare a teaching sequence so that at the end, at the result, students would be able to solve some target problem is something natural. From here, I'd like to offer a hypothesis that mathematics teacher might naturally engage in problem posing out of the need to prepare teaching sequences aimed at empowering their students to solve particularly difficult target problems. And here, let me come back to the Olympiad movements. What are these particularly difficult target problems? I'm going to tell you an extreme story, because in one of our studies, we used problems of International Mathematical Olympiad in our work in teacher education. An idea was that mathematics teachers can probably become brokers between the regular and the Olympiad mathematics if they properly engaged in high level, in advanced mathematics that appears in International Mathematical Olympiad. Specific research questions that we pursued in our small study was, while collaboratively designing instructional sequences for making IMO level problems more feasible to regular students, what problems do the pre-service teacher pose on their own, and how does it take place? Well, all these are nice words, but let me go to specifics. I'm going to talk about a very special situation. I had the pleasure of teaching a course called Advanced Workshop in Teaching Mathematics for Secondary School Mathematics Teachers with a very special group of students. These were 9 practicing teachers who pursued their graduate degree, and they all had quite strong mathematical backgrounds. No one of them, however, was engaged in Olympiad movements or was trained in Olympiad problem solving. On the contrary, they were quite afraid of approaching Olympiad problems. So we worked on problem solving and problem posing ideas and methods and examples for a semester. And at the end of the semester, I offered them an assignment. This is probably the most demanding assignment I ever offered to my students as a teacher. The assignment was of 4 parts. The first part was this: go to the internet and look at the online databases of high-level mathematical Olympiads. International Mathematical Olympiad, the Tournament of Town, and the top-level Israeli Mathematical Olympiad, which is Gillis Olympiad. As we all know, all these materials are open in the internet, and you can find all the problems of IMO with their solutions easily. So look at these problems and choose out of them about 3 problems as target ones. Explain your choice. Well, of course, these teachers and of course their students would not be able without preparation to independently solve these problems. But with proper time, they can understand their solutions. They can work and understand steps of these solutions and ideas if there are no time limitations. So the second part was designing a teaching sequence that would be instrumental in order to enable regular students. Regular students are referred to as high school students of, let's say, good background, but without special preparation for mathematics competitions. So create for them a sequence of lessons, the goal of which is to just understand solution of the chosen problem and or empower them to solve. Again, at IMO, 3 problems are supposed to be solved by the competitors under strict time constraints. No time constraints here, no competition here, just engage with this mathematics. Well, the third part was so-called post-implementation problems, post 3-5 problem that would require the students to implement the knowledge taught present the possible solution to each problem, and explain how these problems are related to the target problems and problems with the sequence. And part number 4, a very, very detailed reflection. Again, it was admittedly the most demanding task I allowed myself to give my students, and they had the entire summer break to finish it. Well, let me exemplify. 9 students worked in 3 teams of 3. And here you see the choice of one of these teams. At stage 1 of the work, the students browsed the collection of Olympiad problems and decided to concentrate on number theory problems from high-level Olympiads. Another group chose geometry, and the third group chose solid geometry. But for the sake of illustration, I present only findings from this team A. These 3 problems, first of all, are quite short, and their solutions are quite short. We know that not every IMO problem has a short solution. The students explained that these 3 problems require consideration of different cases and elimination of some of them by different criteria. And they wanted to create a teaching sequence which a pedagogical goal would be to teach students to consider different cases and use the method elimination, a very proper educational goal. Let me zoom in one of the problems of the 3. So this is just copy-paste from the website of International Mathematical Olympiad, which presents the problem and its solution. We, of course, don't have time, or it's not needed now, to delve into the specific solution of this problem. But from the students' work, we learned that this problem requires knowledge of many kinds. Knowledge to connect Vieta formulas, modular arithmetics, properties of prime numbers, completing to a rectangle as an analogy of completing to a square strategy. And only if students know all this, they can effectively divide the problem into cases. Well, it's quite accurate summary of what is needed in order to solve this problem. And as an example, what they did, they split this solution step by step and thought about prerequisites for the students. They should be taught modular arithmetic. They should be taught Vieta formulas. They should be taught a particular method. As an example, the last solution step includes a seemingly simple algebraic manipulation, which reminded to the students a process of completing the square, as we do when we prove the formula of solving quadratic equations. As an example, I'd like to show that this particular step in the problem solution was a trigger for so-called completing the square problem that this teacher composed as part of their instructional sequence. An idea is actually here to prove geometrically that x squared plus bx equals this, the difference of squares. But in relation to the solution to this IMO problem, it's of course an overkill, but they are teachers. They think about the needs of their students. They have a rich pedagogical agenda. So they compose this 4-part problem, which begins from actually step-by-step illustration of the proof in geometric way, goes to the next case, but this yellow rectangle are invitations for the students to fill them in. There are no yellow rectangles in the first version, just an example. But in the second one, they want the students to be a bit more independent. And then they go to the next case and want the students to be a bit more independent. And finally, the case which is isomorphic to what we have in the solution of this Olympiad problem, they want the students to construct the entire solution. In my view, beautiful, beautiful idea. It's not an Olympiad problem. It's not something that you can put in exam, but in a lesson, why not? And it was an original problem posed by these teachers. An additional example. This is the second problem of the three that they choose. Again, we don't need to go in depth in this problem, but simply put, it is a problem that asks to find all sets of six consecutive integers with a particular property. The solutions are brief, and the first one relies on actually quite straightforward logic. We can eliminate cases and prove that there are not such sets. But the second solution is based on Wilson theorem that the students actually knew from their number theory course. So what can be triggered by such a thing? This time, one of the participants was amazed by an idea that somebody dares to ask a question with no positive answer. Find all such sets, but there are no such sets. And this idea was so engaging to her that she created a so-called shower problem. It's worth reading. Yotam is a child who hates to shower, and this issue leads to frequent argument with his mother. Yotam suggests that his mother establish a clear rule for determining days when he must shower without any argument and implement this rule during the coming year. He suggests, let's enumerate all days of the coming year from 1 to 365. In any day of your choice, my dear mom, you can determine the shower days for me for the next 10 days as follows. You split these 10 days into two sets of days, the shower days and no shower days as you wish. There is only one constraint. The product of the numbers of the shower days must be equal to the product of the numbers of the no shower days. If, for any reason, you cannot meet this constraint, it will be up to me to shower or not during these 10 days. Yotam's mother was glad to see that her son makes an effort to avoid future argument and accepted his suggestion without much thinking. The question is, what is the minimum and the maximum number of the shower days for Yotam during the year according to the suggested rule? Justify your answer. Well, this problem is isomorphic to the initial problem. So the answer is that mom loses. She cannot suggest such a set of days. Mathematically, the problem is isomorphic to this Olympiad problem. The mathematical part, the creative, the literature part was to create an engaging story. But mathematical part was to look for another number, because here we talk about six consecutive numbers, and here she introduced 10 days sets. Why it's interesting? Because to do so, just to substitute the number, she deeply entered to the Wilson theory. So I would not suggest that this problem can be used in some competition, because it's not an original problem mathematically. But I have no doubt that by creating this problem, that teacher deeply understood the solution to the Olympiad problem and somehow adapted it. My time is almost over, and I finish with a brief overview of the findings. In these works, the teachers posed many problems, tens of problems, some of them within sequences and some of them as implementation problem. They can be categorized as guided exploration, diagnostic questions, problems related to particular step of the solution, or story problems isomorphic to the target problem, as I showed right now. What is interesting is the process. How did problem solving take place? If we'll read this long quotation, we'll see that the process was highly instructive for the teachers. They actually began do what problem-solving experts do. Tomorrow we'll probably hear from Igor Kontorovich that problem-solving experts frequently begin from discovering an interesting mathematical phenomenon and then wrapping it up in a story. and novice problem solving do not look for interesting phenomena. Somehow it worked for the students. So in conclusions, I'd like to offer 4 claims. First of all, good news for the Olympiad movement. Under certain very special circumstances, they can do it. Teachers can act as brokers between regular mathematics and Olympiad mathematics. With respect to teacher education, we have a lot of evidence how much they learned, both mathematically, epistemologically, and pedagogically while being engaged in such a task. More generally speaking, the trick is not IMO problems, but the trick is to choose mathematics that would be challenging not only for students, but for the teachers themselves. While studying this challenging mathematics, they can do many things, including learning advanced mathematics, engaging in advanced problem solving, and it can trigger problem posing. Ellerton talked about so-called problem posing pedagogies, like we have problem solving pedagogies, like how to teach via problem solving. We need to have problem posing pedagogies. And this small experiment convinced at least me that problem posing can be promoted adidactically, which means that it can be an implicit objective of an activity having a different explicit goal. In this case, in case of these tasks, the trick was to create a situation in which the teacher could not find ready-made problem for the use, but they need to create a sequence, so they engaged in meaningful problem posing. And of course, the main conclusion from this small scope study is more research about this brokering and about connection of mathematical Olympiads and regular mathematics curriculum is needed. Many thanks, and further details you can find here. I'll leave this slide for a moment on the screen. Thank you very much.
Thank you, Boris, for this very interesting presentation.